in the final part of this chapter we're going to look at what's called the order algorithm. Now the order algorithm is to do with its complexity, and it tells you how the size of a problem affects the time taken to complete the algorithm, and that's often known as the runtime. So the order algorithm comprises a function of its size. So say if we had a size n, so f of n, and we increase that problem, the size of the problem, to n, so it goes up to f of n, then the runtime will increase by a factor of approximately fn over fn. Now, if we consider for a second the bubble sort, now if you say you've got numbers, say 6, 5, 4, 3, 2, 1, and we want the bubble sort to order it in ascending order. So in the first pass, the 6 would move to the end, second pass the 5 would move to the end. So the first pass you would need 5 comparisons, a maximum of 5 comparisons. In the second pass you would need 4 comparisons, third pass you'd need 3, next pass you'd need 2, and the final pass you'd just need 1 comparison. So let's extend that to say you've got n numbers. So in the first pass you'd need n minus 1, then we'd need n minus 2, then we'd need n minus 3, then we'd need n minus 4, all the way down to 3 comparisons, 2 comparisons, 1 comparison. And the number of steps in the algorithm is its size, the maximum number of steps. So if I just reorder that and write it at 1, 2, 3, 4, n minus 1, n minus 2, n minus 3, we add them together. So that would be the total number of steps, which I've written down twice. Let's say I add those together. So 2 lots of the sum would be n minus 1 plus 1 is n minus 2 plus 2 is n, 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 n. And we would have n minus 1 lots of them. So twice the sum would be n times n minus 1. So half that, the total number of steps would be half n minus 1. Now if I were to expand that out, that's a half n squared minus half n. Lead power is 2, so we'd say the bubble sort has a quadratic order. So in a bubble sort, say for example we extended the problem from 6 numbers to 60 numbers, that's increased by a factor of 10. Because it's a quadratic order, the runtime would increase by 10 squared, 100. Okay, let's look at example 17. Now, example 17, we have a flowchart which we'll need to refer to, and we start off with a number, we input that number, we let a equal to, is n divisible by I? Yes, then we say the answer is I. No, we say is a less than square root of n? No, we stop. If yes, we say a equals a plus 1 and keep repeating the iteration all through. Describe what the algorithm does. Well, what the algorithm is doing here is testing whether or not the number is prime. Box A would be n is not prime, box B would be n is prime. Now, it asks to look at the order of the algorithm. Now remember about the order, think about the maximum number of steps required. So what we're going to do is keep testing numbers. A is 1, A is 2, A is 3, A is 4, all the way up to the square root of n. So the maximum number of steps would be the square root of n. So that would be what would say to order. It would have an order of root n. Most of the algorithms we look at on decision have either a linear order, a quadratic order, or a cubic order. Not all of them, most of them. If it's a linear order, then if the size of the problem increases by a factor of k, then so would the runtime. The quadratic order, if it increases by a factor of k, the runtime would increase by k squared. A cubic order would increase, the time taken to complete the algorithm would increase by k cubed. Whether or not you need to learn what the proof for whether or not an algorithm has quadratic, cubic order, etc. is not likely. I think if you was to come up in the exam, you'd be told what order it has, whether it be linear, quadratic or cubic. What you'd need to do is apply that to work out the increased runtime, for example. So let's look at example 18. So we just talked about example 17. Example 18 says we are doing a searching algorithm which has linear order. It says to search a list of 500 values, it takes approximately 0.036 seconds. Estimate the time taken for 1,250. But what we need to do first is look at how the size of the problem has increased. So it's increased from 500 to 1,250. So if we divide them, that tells us it's increased by a factor of 2.5. Because it's a linear factor, that means the runtime will increase also by a factor of 2.5. So the runtime is simply going to be 0.036 times 2.5, which is 0.09. So to go from 500 numbers to 1250 numbers, increase it from 0.03 seconds to 0.09 seconds. I mean, it doesn't seem a lot, this is very, very quick. Okay, on to example 19. Example 19 says we are using a bubble sort in this one, so that's got quadratic order. It takes 0.2 seconds to sort 1,600 numbers using bubble sort. Estimate the time taken for 480,000 numbers. So the size of the problem is increased by 480,000 divided by 1,600. So that's going to be 300. So because it's quadratic order, the runtime is going to increase by a factor of 300 squared, which is 90,000. So if it takes 0.2 seconds for 1,600 numbers, it's going to take 0.2 times 90,000, or just 300 squared, for 480,000, which works out to be 18,000 seconds. So if we divide that by 60, divide by 60 again, we get about 5 hours. So quite a massive increase. Now, interestingly, the other sorting algorithm we could have used was the quicksort. Now the quicksort is an average of order. Now this is going to seem a bit weird, but the quicksort has an order of, on average, of n log n. Now, you haven't come across logs before. You'll do it at the end of the year 1 A-level maths course in the pure section, but it's just something you can smack into your calculator to get an answer. So the runtime is going to increase by a factor of 480,000 log 480,000 divide by 1600 log 1600. If you put that into your calculator, that works out to be approximately 532. So bubble sort increases by a factor, the runtime by a factor of 90,000. Quicksort increases by a factor of 532, which is one of the reasons why quicksort is a more efficient method than bubble sort. But you only really get to feel the benefit of the quicksort when you're dealing with massive numbers. Okay, I think that ends the chapter. So if I go now exercise 1F plus mixed exercise 1.